The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
My name is Aline. I work in Stata, in the Stata Center. I'm a PhD student there in my 5th year. And today we're going to be talking about one of our research projects called Catena. And Catena is a really nice way of using Bitcoin to build append-only logs. Bitcoin itself is an append-only log, and a lot of people have been using it to put data in it. And I'll describe a really efficient way of doing that and its applications. And if there's time, we'll talk about attacks and maybe colored coins and some other stuff. We'll talk about the what, the how, and the why. And that's the overview of the presentation. So let's talk about this problem called the equivocation problem. So what is this? In general, non-equivocation means saying the same thing to everybody. So for example, if you have a malicious service and you have Alice and Bob, the service should say the same thing to Alice and Bob. So it would make a bunch of statements, let's say S1, S2, S3 over time, and Alice and Bob would see all of these statements. So this is very similar to what Bitcoin provides, right? In Bitcoin, you see block 1, block 2, block 3, and everybody agrees on these blocks in sequence, right? Does that make sense? So this is non-equivocation, and in some sense, this is what Bitcoin already offers. And in general, with non-equivocation, what you might get is some of these statements might actually be false or incorrect. Non-equivocation doesn't guarantee you that this statement is a correct statement, but it just guarantees you that everybody sees the same statements, and then they can detect incorrect statements. In Bitcoin, you get a little bit more. You actually know that if this is a block, it's a valid block, assuming there's enough blocks on top of it, right? So equivocation means saying the same thing to everybody. So for example, this malicious service at time 4, he might show Bob a different statement than Alice. So Bob sees S4 and Alice sees S4 prime. This is what happens in Bitcoin sometimes, and that's how you can double spend in Bitcoin, by putting a transaction here, sending money to the merchant, and then putting another transaction here, sending money back to you, right? Are you guys familiar with this? Yeah? Okay. All right, so why does this matter? Let me give you a silly example. Suppose we have Jimmy, and we have Jimmy's mom and Jimmy's dad, right? And Jimmy wants to go outside and play, but he knows that mom and dad usually don't let him play. So what he does is he tells dad, hey, dad, mom said I can go outside, right? And then he tells mom, hey, mom, dad said I can go outside. And let's say mom and dad are in different rooms and they're watching soap operas and they're not talking to one another. So they can actually confirm that, mom can confirm that dad really says that, and dad can't really confirm that mom said that, but they both trust Jimmy. So you see how equivocation can be really problematic, because now mom and dad will say, sure, go outside, as long as the other person said that, right? But let me give you a more practical example. So let's look at something called a public key directory. A public key directory allows you to map users' public keys, a username to a public key, right? So here I have the public key for Alice, and here I have the public key for Bob, and they look up each other's keys in this directory, and then they can set up a secure channel. How many of you guys use WhatsApp, for example? So WhatsApp, the WhatsApp server, has a public key directory, and when I want to send you a message, I look up your phone number in that directory, and I get your public key, right? If that directory equivocates, the following thing can happen. What the directory can do is he can create a new directory at time 2, where he puts a fake public key for Bob, and he shows this to Alice, right? And at time 2 also, he creates another directory for Bob, where he puts a fake public key for Alice, right? So now, the problem here is that when Alice checks in this directory, she looks at her own public key to make sure she's not impersonated. And Alice looks in this version and sees, OK, that is my public key, I'm good. She looks in this version, OK, this is my public key, I'm good. So now I'm ready to use this directory, and I'll look up Bob, and I'll get his public key. But Alice will actually get the wrong public key. Does everybody see that? And similarly, Bob will do the same. So Bob will look in his fork of the directory, right? And he looks up his key here and his key here. And he thinks he's OK, he's not impersonated, but in fact, Alice is impersonated there. OK? And now, as a result, they will obtain fake keys for each other. And this man-in-the-middle attacker, who knows the corresponding secret keys for these public keys, can basically read all of their communications. Any questions about this? This is just one example of how equivocation can be really disastrous. So in a public key directory, if you can equivocate, you can show fake public keys for people and impersonate them. So in other words, it's really important that Alice and Bob both see the same directory, because if Bob saw this directory, the same one Alice saw, then Bob would notice that this is not the public key he had. He would notice his first public key, and then that there's a second one there. And then he would know he's impersonated, and he could, let's say, whistleblow, talk to the New York Times, and say, look, this directory is impersonating me. Right? So in conclusion, equivocation can be pretty bad. So this idea that you say different things to different people can be pretty disastrous. And what Catena does is it prevents that. So in general, if you have this malicious service that is backed by Catena, if it wants to say different things to different people, it cannot do that. It has to show the same thing to everybody. And the way we achieve that is by building on top of Bitcoin. And that's what we're going to be talking about today. So any questions about sort of the general setting of the problem and our goals here? So let's move on then. So why does this matter? So this matters for a bunch of other reasons, not just public key directories and secure messaging. It matters because when you want to do secure software update, equivocation is a problem, and we'll talk about that later. So for example, at some point, Bitcoin was concerned about malicious Bitcoin binaries being published on the web, and people like you and me downloading those binaries and getting our coins stolen, right? And it turns out that that's an equivocation problem. Somebody's equivocating, right? It's equivocating about the Bitcoin binary. It's showing us a fake version and maybe other people a real version. Secure messaging, like I said before, has applications here. And not just secure messaging, but also the web. Like when you go on Facebook.com, you're looking up Facebook's public key. And if somebody lies to you about that public key, you could be going to a malicious service, and you could be giving them your Facebook password. Does that make sense? And also it has applications in the sense that if you have a way of building an append-only log, you really have a way of building a blockchain, right, for whatever purpose you want. And we'll talk about that as well. So the 10,000 feet view of this system is we built this Bitcoin-based append-only log. And the way to think about it is that Bitcoin is already an append-only log. It's just that it's kind of inefficient to look in that log. If you want to pick certain things from the Bitcoin blockchain, like you put your certain bits and pieces of data there, you have to kind of download the whole thing to make sure you're not missing anything. And I'll tell you why soon. So instead of putting stuff naively in the Bitcoin blockchain, we put it in a more principled way. And in this sense, we get a log in another log. We get our log and the Bitcoin log. And this generalizes to other cryptocurrencies. Like you could do this in Litecoin, for example, or even in Ethereum, though I don't think you guys yet talked about how the Ethereum blockchain works. And the cool thing about this Catena log that we're building is that the Catena log is as hard to fork as the Bitcoin blockchain. If you want to fork our log, you have to fork Bitcoin. However, unlike the Bitcoin blockchain, Catena is super efficient to verify. So in particular, remember I described the log in terms of the statements in it. So if you have 10 statements, each statement will be 600 bytes to audit. So you don't have to download the whole Bitcoin blockchain to make sure you're not missing a statement. And you also have to download 80 bytes per Bitcoin block. And we have a Java implementation of this. And if you guys are curious, you can go to my GitHub page and take a look at the code. All right, so before we start, I know you guys already know a lot about how the Bitcoin blockchain, but it's important that I reintroduce some terminology just so we're on the same page. So this is the Bitcoin blockchain. We have a bunch of blocks connected by hash chain pointers, and we have Merkle trees of transactions. And these arrows indicate hash pointers. It means that block n stores a hash of block n minus 1 in it, right? So that in that sense, block n has a hash pointer to block n minus 1. All right, and like I said, each tree has a Merkle tree, each block has a Merkle tree, and everybody agrees on this chain of blocks via proof of work consensus, which all of you already know. And importantly, in the Merkle trees, we have transactions, and transactions can do two things, right? A transaction can mint coins, create new coins. So here I have transaction A. It created 4 coins by storing them in an output. Are you familiar with outputs? So you guys already discussed transaction outputs and inputs, so that's what we're going over here again real quick. So an output specifies the number of coins and the public key of the owner of that coins, as you already know. And the second purpose of transactions is that they can transfer coins, right, and pay fees in the process. So here, if you have a transaction B, this transaction B might say, hey, here's a signature from the owner of these coins here. Here's a signature in transaction B. And here's the new owner with public key B of 3 of those 4 coins. And one of those coins, I'll just give it to the miners as a transaction fee. Does this make sense? How many of you are with me? All right. Any questions about how transaction inputs and outputs work? So if you remember in the input here, you have a hash pointer to the output here. Right? And the high-level idea here is that the output is just a number of coins and a public key, and the input is a hash pointer to an output plus a digital signature from that output's public key. Okay? And yeah, so what happens here is that transaction B is spending transaction A's first output. Right? That's the terminology that we're going to use, and I think you guys have already used terminology like this. And in addition, what we're going to talk about today is the fact that in these Bitcoin transactions, you can actually embed data. And I think you touched briefly on this concept of op return transaction outputs, right? So this is an output that sends coins to a public key, but here I can have an output that sends coins to nobody. It just specifies some data. And in fact, I'll use that data to specify the statements that I was talking about earlier. So the high-level point here is that you can embed data in Bitcoin transactions using these op return outputs. And there's a bunch of other ways to do it, actually. Like initially, what people did is they put the data as the public key. They just set the public key to the data, and in that sense, they kind of wasted Bitcoins, right? They said, hey, send these 3 Bitcoins to this public key, which is just some random data, but nobody would know the corresponding secret key of that public key. So that therefore those coins would be burned. Did you cover this in class already? Maybe a little bit. So, but that's kind of inefficient, because if you remember, the miners have to build this UTXO set, and they have to keep this output that has this bad public key in their memory forever, because nobody's going to be able to spend it. So we don't want to do that. We want to build a nice system, a system that treats Bitcoin nicely, the Bitcoin miners. So that's why we use these op return outputs. All right, so the high level here is that Alice gives Bob 3 Bitcoins, and the miners collect a Bitcoin as a fee. And of course, you can keep doing this, right? Like Bob can give Carol these 2 Bitcoins later by creating another transaction with an input referring to that output, and with an output specifying Carol's public key. All right, and the high-level idea of Bitcoin is that you cannot double spend coins. And what that means is that a transaction output can only be referred to by a single transaction input. So this thing right here in Bitcoin, where I have 2 inputs spending an output, cannot happen, right? How many of you are familiar with this already? Okay, good. So actually, this is the essential trick that Catena leverages, and we'll talk about it soon. And yeah, the moral of the story, the reason I told you all of this is because basically, if you have proof of work consensus in the Bitcoin sense, you cannot do double spend. So this thing right here that I said before just cannot occur in the Bitcoin blockchain unless you break the assumptions, right? Unless you have more mining power than you should. In that case, you'll either have TX2 or TX2 prime, but not both, right? And what Catena really realizes is that if I put statements in these transactions now, what that means is that I can only have a second statement. I cannot have 2 second statements. I cannot equivocate about the second statements if I just restrict my way of issuing statements in this way. I put the first statement in the transaction, and the second statement I put it in a transaction that spends the first one. So does everybody agree that if I do things in this way and I want to equivocate about the second statement, I would have to double spend? So that's the key insight behind our system. Any questions about this so far? It's really hard to talk. If you guys talk back, it's way easier. So yeah.
Question. So, and maybe I think I'm getting this right, but if you're setting up the first transaction and then you're adding data on, like you're burning Bitcoins every time you're doing it. So at some point you run out.
That's an excellent question. So we'll go over that. But the idea is that in this output, I won't burn any Bitcoins. I'll actually specify my own public key here. And I'll just send the Bitcoins back to myself. And in the process, I'll pay a fee to issue this transaction. Does that make sense? Yeah. And we'll talk about it later. OK. So real quickly, what did previous work do regarding this? So how many of you are familiar with Blockstack? 1, 2, only 2 people? OK. How many of you are familiar with Keybase? OK, so Blockstack and Keybase actually post statements in the Bitcoin blockchain. And they're both public key directories. They map usernames to public keys. And for example, Keybase, what Keybase does is they take this Merkle root hash, and they put it in a transaction. And then 6 hours later, they take the new root hash, and they put it in another transaction, and so on. Every 6 hours, they post a transaction. But unfortunately, they don't actually do what Catena does. So they don't have their new transactions spend the old one. And as a result, if you're trying to make sure you see all of the statements for Keybase, you don't have a lot of recourse other than just downloading each blockchain, each block, and looking in the block for all of the relevant transactions. Another thing you could do is you could sort of trust the Bitcoin miners, the Bitcoin full nodes, to filter the blocks for you. So you could say, you could contact a bunch of Bitcoin full nodes and say, look, I'm only interested in transactions that have a certain app return prefix in the data. And they could do that for you, but unfortunately, Bitcoin full nodes could also lie to you very easily, and there's no cost for them to lie to you. Everybody can be a Bitcoin full node. So then it becomes a very bandwidth-intensive process because you have to ask a lot of full nodes to deal with the fact that someone might lie to you. So you either need to download full blocks to find, let's say, a missing statement like this one that a Bitcoin full node might hide from you, or you can trust the majority of Bitcoin full nodes to not hide statements, which is not very good, right? So I don't want to trust these full nodes because all of you guys could run a full node right now in the Bitcoin network. It doesn't cost you anything. And if I talk to your malicious full nodes, I could be screwed. So our work just says, look, instead of issuing transactions in a sort of uncorrelated fashion, just do the following thing. Every transaction you issue should spend the previous one. So as a result, if someone wants to equivocate about the third statement, they have to double spend, like I said before. Right? Yeah.
So what's the connection back to Keybase and Blockstack again?
Yeah, so Keybase Keybase and Blockstack are public key directories, and what they do is they want to prevent themselves from. Is there a whiteboard I can draw here? Yeah. So let's say. If you remember the picture from the beginning, I can have a public key directory that evolves over time, right? So this is V1 of the directory, and it might have the right public keys for Alice and Bob. But at V2, the directory might do this. It might do V2, it might have Alice, Bob, but then put a fake key for Alice. And at V2 prime, it might do Alice, Bob as before, and put a fake key for Bob. So in other words, it keeps the directory append only, but it just adds fake public keys for the right people in the right version. So here, this one is shown to Bob, and here, this one is shown to Alice. So now Alice will use this fake key for Bob, so she'll encrypt a message with B prime for Bob, and now the attacker can easily decrypt this message because he has the secret key. So what the attacker can do then is re-encrypt it with the right public key for Bob, and now he can read Alice's messages. And the whole idea is that the attacker, this B prime is the public key, is a PK B prime, let's say, but the attacker has SK B prime. He knows SK B prime because the attacker put this in there. The attacker being really Blockstack or Keybase. And of course, they're not attackers in the sense that they want to be good guys, but they're going to be compromised eventually, so they want to prevent themselves from doing things like these. Does that sort of answer your question? Yeah. All right. So yeah, really simple summary. If I had 2 slides to summarize our work, this would be it, right? It would be these 2. Like, look, don't do things this way, do them this way, right? So let's look a little bit at the design. So remember, we have these authorities that could equivocate about statements they issue, like Blockstack or Keybase. So what we propose is, look, these authorities can run a lock server, a Catena lock server. They start with some funds locked in some output. And what they can do first is they can issue this Genesis transaction to start a new log. So for example, Keybase would issue this Genesis transaction starting the log of their public key directory Merkle roots. And this Genesis transaction can be thought of as the public key of the log. Once you have this Genesis transaction, you know its transaction ID, you can verify any future statements, and you can implicitly prevent equivocation about statements. And what the log server is going to do is it's going to take these coins and send them back to the server to answer your question. So if there was a public key, if these coins are owned by some public key, they're just sent back to the same public key here and paying some fees in the process. Right? So we're not burning coins in the sense that we're just paying fees to the miners, which we have to do. OK, so now what you can do is if you want to issue the first statements, you create a transaction. You send the coins from this output to this other output. You pay some fees in the process. You put your statement in an op return output. And And as a result, if this lock server wants to equivocate, it has to, again, double spend here, which it cannot do unless it has enough mining power. So Keybase and Blockstack, if they were to use a system like this, they could prevent themselves from equivocating. And this can keep going, right? So you issue another transaction, spend the previous output, put the new statement. Yes?
This doesn't seem like a new problem. How have authorities prevented equivocation in the past?
This doesn't seem like a new problem. How did authorities do it? The problem is not new. The problem is eternal. So you are correct there. How did they do it in the past? They just used a Byzantine consensus algorithm. So in some sense, this is what we're doing here as well. We're just piggybacking on top of Bitcoin's Byzantine consensus algorithm.
So you're rolling down to a newer Byzantine consensus algorithm, basically.
Sure, I'm not sure what rolling down means, but yeah, we're piggybacking on top of Bitcoin. The idea is that, look, a Byzantine consensus is actually quite complex to get right. We already have a publicly verifiable Byzantine consensus algorithm. It's Bitcoin. Why can't we use it to verify, let's say, a log of statements super efficiently? So up until our work, people didn't seem to do this. So Keybase didn't do this, Blockstack didn't do this. They kind of forced you to download the entire Bitcoin blockchain to verify, let's say, 3 statements. So in our case, you only have to download a few kilobytes of data to verify these 3 statements, assuming you have the Bitcoin block headers, right? Which we think is a step forward. And it's sort of like the right way to use these systems should be, the efficient way, not the inefficient way, because bandwidth is expensive, right? Computation is cheap, bandwidth is expensive. All right. So anyway, the idea is that if the lock server becomes malicious, if Keybase or Blockstack gets hacked, they cannot equivocate about the third statement. They can only issue one unique third statement. And the advantages are, it's hard to fork this lock. It's hard to equivocate about the third statement, but it's efficient to verify. And I'll walk you through how clients verify soon. The disadvantages are that if I want to know that this is the second statement in the log, I have to wait for 6 more blocks to be built on top of this statement's block, right? Just like in Bitcoin, you have to wait for 6 blocks to make sure a transaction is confirmed, right? Why do you do that? The reason you do that is because there could be another transaction here, double spending, because sometimes there are accidental forks in Bitcoin and things like that. What are some other disadvantages that you guys can point out? Yeah?
It's like an expensive server.
It's going to be expensive to issue these transactions. So Aline and I share the same name. So Aline is pointing out that every time I issue these statements, I have to pay a fee, right? And if you remember, the fees were quite ridiculous in Bitcoin. So that's a problem, right? So let's see, was that the next thing? No, the next thing was you can only issue a statement every 10 minutes, right? So if you want to issue statements really fast, you can't do that, all right? Like Aline said, you have to issue Bitcoin, you have to pay Bitcoin transaction fees. And the other problem is that you don't get freshness in the sense that it's kind of easy for this lock server to hide from you the latest statement. Unless you have a lot of these lock servers and you ask many of them, hey, what's the latest statement? And they show you a Merkle path to the latest statement. If there's just one lock server and it's compromised, it could always pretend, no, this is the latest statement. And if you don't trust it, the best recourse you have is to download the full block and look for the statement yourself. So you don't get freshness. Those are some disadvantages. Now, let's look at how clients audit this lock. So I was claiming that it's very efficient to get these statements and make sure that no equivocation happened. So let's say you have a Catena client and you're running on your phone with this client and your goal is to get that list of statements. And there's the Catena lock server over there in the back. And there's the Bitcoin peer-to-peer network, which at the moment has about 11,000 nodes. And remember I said the first thing you need is the Genesis transaction. Does everybody sort of understand that if you get the wrong Genesis transaction, you're completely screwed, right? Because it's very easy to equivocate if you have the wrong Genesis transaction, right? I mean, there's the right GTX here, where you have, let's say, S1, and then you have S2 in their own transactions, right? But if there's another GTX prime here, and you're using that one, you're going to get S1 prime, S2 prime, a different statement. So if Alice uses GTX, but Bob uses GTX prime, Alice and Bob are back to square one. So in some sense, you might ask, OK, so then what's the point? What have you solved here? I still need to get to this GTX, right? So what we claim is that this is a step forward because you only have to do this once. Once you got this GTX, you can be sure you're never equivocated to, right? Whereas in the past, you would have to, for each individual statement, you would have to do additional checks to make sure you're not being equivocated to. Like you would have to ask enough full nodes, let's say. Right? So as long as you have the right GTX, you're good. And how do you get the right GTX? Well, usually you ship it with the software on your phone. And there's some problems there as well. Like there's no problem solved in computer science in some sense, but we're trying to make progress here. Okay, so let's say you have the right GTX because it got shipped with your software. Now the next thing you want to do is get the block headers. So you have header I, but there are some new headers being posted. Let's say the Bitcoin peer-to-peer network sends them to you. You have these headers, you verify the proof of work, right? So this only costs you 80 bytes per header, right? Does everyone see that this is very cheap? So far I have the GTX, which is, let's say, 235 bytes. And now I'm downloading some headers. And now I'm ready to ask the log server, what's the first statement in the log, right? And what the log server will do is he's going to reply with the transaction with the statement, which is 600 bytes, and the Merkle proof. So all of this is 600 bytes, actually, right? And now what the Catena client will do is he'll check the Merkle proof against one of the headers. So to see in which headers does it fit. And then he'll also check that the input here has a valid signature from the public key in the output here. All right. I want at least one question about this. Yeah?
Sorry I came in late, but is the Catena client over there similar to an SPV or something like that?
Yeah, so that's exactly. It's an SPV client. Yeah. So the idea is that we want SPV clients. We don't want these mobile phone clients to download 150 gigabytes of data. We want them to download, let's say, 40 megabytes worth of block headers, which they can discard very quickly as they verify. And then we want them to download 600 bytes per statement. But still be sure that they saw all of the statements in sequence and that there was no equivocation. Yeah? Yeah?
So in our previous classes, we discussed the difference between having a full node and an SPV node. Do these sort of vulnerabilities exist in the Catena client?
So which vulnerabilities did you talk about?
I forget.
Did you talk about...
there was just a box that was like less secure, and
yeah.
then there's another box that was like something else bad.
What about like which I was thinking about some things, the clients can lie to you, right? About like if you say, well, here's some transactions or here's some unspent outputs, and they could just tell you something different.
Yes, yeah, sorry.
Well, they can't tell you transactions exist that don't exist. They can just not tell you.
Or not, yeah, sorry.
Yeah, they could hide transaction from you, which gets back to the freshness issue that we could discuss. They could also, this block header could be a header for an invalid block. But remember that before you accept this TX1, you wait for enough proof of work. You wait for more block headers on top of this guy to sort of get some assurance that, no, this was a valid block because a bunch of other miners built on top of it, right? So as long as you're willing to trust that the miners do the right thing, which they have an incentive to do the right thing, you should be good. But like you said, what's your name? Anne, like Anne said, there are actually bigger problems with SPV clients, and if there's time we can talk about it, but it's actually easier to trick SPV clients to fork them. And there's something called a generalized vector 76 attack. Have any of you guys heard about this? So it's like a pre-mining attack, but it's a bit easier to pull off. Actually, it's a lot easier to pull off on an SPV node than on a full node. And if there's time at the end, we can talk about it. If there isn't, you can read our paper, which is online on my website, and you can read about these pre-mining attacks that work easier for SPV nodes. But anyway, this can keep going, right? You get block headers, 80 bytes each. You ask the log server, hey, what's the next statement in the log? You get a Merkle proof and a transaction, and then you verify the Merkle proof. You put this transaction in one of these blocks, and you verify that it spans the previous one. Right? And as a result, you implicitly, by doing this verification, by checking that, hey, this is a transaction in a valid block, this block has enough stuff built on top of it, and this transaction spends this guy here, you implicitly prevent equivocation. Right? And you don't have to download anything else. Right? You only have to download these Merkle proofs and transactions and these block headers. Whereas in previous work, you could be missing these S1s, these S2s. They could be hidden away in some other branch of the Merkle tree. And you would have to do peer-to-peer Bloom filtering on the full nodes. And those full nodes could lie to you. Yeah, so the bandwidth is actually very small. So suppose we have 500K block headers. I think Bitcoin has a bit more right now, which are 80 bytes each. And we have 10,000 statements in this log. which are 600 bytes each, then we only need to download 46 megabytes, right? What's the other way of doing it? You have to download hundreds of gigabytes. All right, so let's talk about scalability a little bit. So suppose this system gets deployed widely. Let's say WhatsApp starts to use the system to to publish their public key directory in Bitcoin, right? And everybody, a lot of you here have WhatsApp, and this is you guys. Let's say there's 200,000 people using WhatsApp. I think there's more like 1 billion. So what are they going to do? Remember that part of the verification protocol is asking for these block headers from the peer-to-peer network, right? And in fact, if you're a SPV client, you usually open up around 8 connections to the peer-to-peer network. And if you're a full node in the Bitcoin peer-to-peer network, you usually have around 117 incoming connections. That's how much you support. You support 117 incoming connections as a full node. So that means in total, you support about 1 million incoming connections. So this guy supports 1 million, but we need about 1.6 million connections from these 200,000 clients, right? So it's a bit of a problem if you deploy Catena and it becomes wildly popular. Being a bit optimistic here, but let's say that happened, right? So how can we fix this? How can we avoid this problem? Because in this case, what we would basically be doing is we would be accidentally DDoSing Bitcoin, and we don't want to do that. Does everybody see that there's a problem here, first of all? Yeah. Okay, so the idea is very simple. We just introduced something called a header relay network. And what that means is, look, you don't really have to ask for these block headers from the Bitcoin peer-to-peer network. You could just outsource these block headers anywhere, because they're publicly verifiable, right? The block headers have proof of work on them. So you can use volunteer nodes that sort of push block headers to whoever asks for them. You could use blockchain explorers like blockchain.info, right? You could use Facebook. You could just post block headers on Facebook, right? Like in a Facebook feed. You could use Twitter for that. You could use, I don't know, GitHub gists, So there's a lot of ways to implement this. The simplest way is have N servers and have them send these headers to whoever asks for them. So it's easy to scale in that sense, because if you now ask this header relay network for the block headers, it's much easier to scale this than to scale the Bitcoin peer-to-peer network, which has to do a bit more than just block headers. They have to verify blocks. They have to verify signatures. Yeah.
Did you consider having the clients be peer-to-peer?
Yeah, so another way, and I think we talk about that in the paper, is you can implement the header relay network as a peer-to-peer network on top of the clients. Yeah. So that's another way to do it. There's some subtleties there that you have to get right, but you can do it, I think. Yeah?
Wouldn't you expect that if a company like WhatsApp decided to adopt Catena, they would run their own servers to make sure that there was the capacity for it?
For the header relay network?
Yes.
I mean, I would just be speculating, wishful thinking. They could. There is some problem with this header relay network as well, and we talk about it in the paper, because this header relay network could withhold block headers from you. So you do have to distribute it. Like, usually you don't want to just trust WhatsApp, who's also doing the statements, who's also pushing the statements in the blockchain. You don't want to trust them to also give you the block headers. You actually want to fetch them from a different source that WhatsApp doesn't collude with. Yeah, Anne, you had a question.
Are there other header relay networks that are deployed already?
Yeah, there's actually one on Ethereum. There's a smart contract in Ethereum. I think that if you submit Bitcoin block headers to it, you get something back, and then you can just query Bitcoin block headers from the Ethereum blockchain. Is anyone familiar with this? So I guess I didn't include it here, but another way to do it is to just publish the headers in an Ethereum smart contract. Yeah. So there's crazy ways you could do this too. Yeah.
Will that one run out of gas? I don't know. My understanding of Ethereum is pretty nascent, but would that smart contract eventually run out of gas and not publish anymore?
So to fetch from it, you don't need to pay gas. Okay, but I suspect to push in it, I actually don't know who funds that contract. So I guess you fund it when you push, maybe not, because then you also want something back. Why would you push? I'm not sure, but we can look at it after. Yeah, it's a good question. So anyway, even if this header relay network is compromised, if you implement it in the right way, you distribute it on a sufficient number of parties, you can still get all of the properties that you need to. meaning freshness for the block headers. That's really the only property that you need to. The header relay network should always reply with the latest block headers. So let's look at costs, since Aline was mentioning the costs. So to append a statement, you have to issue a transaction, right? And the size of our transactions are around 235 bytes. So, and the fee as of December 13 was $1624 per transactions, if you guys remember those great Bitcoin times. I think that it went up to 40 at some point too. So it was very hard for me to talk to people about this research back then. But guess what the fees are today? So today, this morning, I checked, and they're 78 cents, right? When we wrote the paper, they were like 12 cents. So, you know, here I am standing in front of you, pitching our work. In 2 minutes, they could be back to $100, but who knows? Yes, you had a question.
Maybe I'm wrong, but in a transaction, you can have several outputs. Can you have several statements in there?
So that's a good question. So can you batch statements? And the answer is yes, you can definitely batch statements. What we said so far is in a transaction, in a Catena transaction, you have this output, and you have this op return output where you put the statement, right? And you know, it spends a previous transaction. But as a matter of fact, what you can do, and some of you may already notice this, is there's no reason to put just one statement in here. There is some reason. So the only reason is that it only fits 80 bytes. So you could put easily, let's say, 2 or 3 statements in there if you hash them with the right hash function. But a better way to do it is, why don't you put here a Merkle root hash, and then you can have as many statements as you want in the leaves of that Merkle tree, right? In fact, here you could have, I don't know, billions of statements. So keep in mind, you will only be able to issue billions of statements every 10 minutes, but you can definitely have billions of statements in a single transaction if you just batch them. So now, remember, the blockchain will only store the root hash. This Merkle tree will be stored by the lock server, perhaps, or by a different party. They don't have to be the same party. Does that make sense? Does that answer your question? Yeah? All right. So that was my next point. Statements can be batched with Merkle trees. OK, so let's talk about the why, since so far we've been talking abstractly about these statements. But what could these statements actually be? So let's look at a secure software update. So how do you do secure software update? An example attack on a software update scheme is that somebody compromises the bitcoin.org domain. And they change the Bitcoin binary to a malicious binary, and they wait for people to install that malicious binary. And then they steal their coins, they steal their data, they could execute arbitrary code. And an example of this was sort of this binary safety warning on the Bitcoin website. At some point, they were very concerned that a state actor is going to mess with the DNS servers and redirect clients to a different server and make them download a bad Bitcoin binary. So does the attack make sense? Does everybody see why this is possible? You do need to sort of accept that the DNS service that we currently have on the internet is fundamentally flawed. It's not built for security. So the typical defense, the typical defense for this is that the Bitcoin developers, they sign the Bitcoin binaries with some secret key, and they protect that secret key. And then there's a public key associated with the secret key that's posted on the Bitcoin website, right? And maybe some of you will notice that sometimes it's also very easy to change the public key on the website, you know, if you can just redirect the victim to another website. And another problem is that not everyone checks the signature. Even if, let's say, you have the public key on your computer, you know what the right public key is. Only if you're like an expert user and you know how to use GPG, you will check that signature, right? And the other problem that's probably, I think, much bigger of a problem is that for the Bitcoin devs themselves, it's very hard to detect if someone stole their secret key. Like if I'm a state actor and I break your computer and I steal your secret key, I will sign this Bitcoin binary and I'll give it to, let's say, one guy. I'll give it to you, you know, and I'll just target you individually because I'm really, you know, I know you have a lot of Bitcoin, right? And then the Bitcoin devs will never find out about it. Unless, you know, you kind of realize what happened, then you take your Bitcoin binary and you go with it to the Bitcoin devs and they check the signature and they say, oh, wow, this is a valid signature and we never signed it, so somebody must have stolen our secret key. So this is really a bad kind of the core of the problem is that it's hard for whoever publishes software to detect that their secret key has been stolen, to detect malicious signatures on their binaries. Does that make sense? So a solution, of course, is publish these signatures of Bitcoin binaries in a Catena log. So now if there's a malicious binary being published by a state actor, people won't accept that binary unless it's in the Catena log, which means people and the Bitcoin devs will see the same binary. Right? So let me show you what I mean with a picture. So we have this Catena log for Bitcoin binaries. And let's say the first transaction has a hash of the Bitcoin 0.001 tar file, right? The Bitcoin binaries. And this hash here is implicitly signed by the signature in this input, because it signs the whole transaction. Right? So now if I put this hash in a Catena log, I get a signature on it for free. And now if, let's say, a state actor compromises the log server, gets the secret key, he can publish this second malicious binary in the log, right? But what that malicious state actor will want to do, he will want to hide this from the Bitcoin devs and show it to all of you guys, right? So he'll want to equivocate. So as a result, he will want to create a different transaction with the right Bitcoin binary there, show this to the Bitcoin devs while showing this to you guys, right? So the Bitcoin devs would think they're good, this is the binary they wanted to publish, while you guys would be using this malicious binary published by the state actor. Of course, this cannot happen because in Catena you cannot equivocate, right? Does everybody see this? Right? Any questions about this? There has to be a question on this. No? So this mechanism is called software transparency. It's this idea that rather than just downloading software like a crazy person from the internet and installing it, we should just be publishing these binaries in a log that everybody can see, including the software vendors that created those binaries. So in this way, if somebody compromises a software vendor, that vendor can notice that in the log there's a new version for their software that they didn't publish. So, this isn't to say that it'll prevent attacks. What a state actor can do anyway is they can just do this. They can post this H2 prime in here, show it to you guys, including the Bitcoin devs, right? And still screw everyone over. But at least these attacks don't go undetected anymore, right? So it's a step forward in that sense. Yes, so the idea is that you have to double spend to equivocate. And the other example that really, the reason I wanted to start this research had to do with public key distribution. So let's say we have Alice and we have Bob. And they both have their public keys. And I'm using this letter B to denote Bob and his public key, and the letter A to denote Alice and her public key. And they have their corresponding secret keys, right? And Alice and Bob, they want to chat securely, right? So they want to set up a secure channel. And there's this directory which stores their public key. So this guy stores Alice, PK Alice. This guy stores Bob, PK Bob, right? And the directory gets updated over time. Maybe Carl, Ellen, and Dan registered. And if you have non-equivocation, if the attacker wants to impersonate Alice and Bob, he kind of has to put their public keys, the fake public keys, in the same directory, which means that when Alice and Bob monitor, they check their own public keys, they both notice they've been impersonated, right? So again, the idea is that you can detect. Now, how can this attacker still trick Alice to send an encrypted message to Bob with Bob's fake public key? Is there a way, even if you have non-equivocation? So what's the attack? Even I have non-equivocation, and I claim that the attacker can still get Alice to send a fake, an encrypted message to Bob that the attacker can decrypt. What should the attacker do? So pretend that we are here, without the ability to equivocate. So the attacker cannot equivocate, but I claim that the attacker can still trick Alice into sending a message to Bob that the attacker can read. All right, so now it's time to see if you guys paid attention. Somebody? Aline. Oh, you. Okay.
Does the attacker have to have the secret key?
No, he does not. Yeah. He does not have to have the secret key. the attacker just creates fake public keys. Here's a hint.
If you only change one person's, couldn't you? They don't know that it's a fake key, so they could send it a fake key for it, and you still.
Yeah. So whose person should the attacker change the key for?
If they change Bob, Alice will still think Bob's is correct, so they'll
Yeah.
send it to the fake Bob until Bob checks it.
Exactly. So that's exactly right. So what's your name?
Lucas.
Lucas. So what Lucas is saying is, look, even without equivocation, I had this directory at T1, I had another one at T2, but at T3, and both of these had keys for Alice and Bob, right? But at T3, Lucas is saying, look, just put a fake key for Bob here, and that's it. Don't put a fake key for Alice there, just for Bob. And now when Alice looks up this public key for Bob here, she sends a query to the directory, hey, what's the Bob's public key? She gets back B prime, which is equal to Bob pk Bob prime, right? Alice can tell if that's really Bob's fake public key. That's the reason she's using the directory in the first place. She wants sort of a trustworthy place to get it from. Bob can tell if Bob looks, but by the time Bob looks, it might be too late. Alice might have already encrypted a message, right? So again, what's the point of doing all of this? It's not like you're preventing attacks, right? And the point of doing all of this is that you get transparency. Bob can detect, whereas right now, Bob has no hope. In fact, so you said a lot of you use WhatsApp. So in WhatsApp, if you really want to be sure, so I have a conversation here with Alin Dragos. So Alin, do you want to bring your phone here? Do you have WhatsApp? So if you really want to be sure that you're talking to the real Alin and not some other guy, you have to go on this encryption tab. Can you tape this? So my phone is black and white. It's going through a depression phase. I apologize. So you have to go here, and there's a code here, right? And Alin, can you do the same thing? You know what I'm talking about?
Let me see.
I really hope I don't get some weird text message right now with the camera on the phone. OK, so now with Alin's phone, is that the same code? Can somebody tell me? I can't see it.
It's hard to say.
OK, so we have 27826 and 2, yeah. So it's the same code. Can you see it on the camera? So now because we have the same code here, what this code here really is a hash of my public key and Alin's public key. And if we got the same hash of both of our public keys, then we know we're talking to one another. But we won't really know that's the case until we actually meet in person and do this exchange, right? So what this system does instead is it allows Alin to check his own public key, and it allows me to check my own public key. This way, if we check our own public key, we'll always know when we're impersonated. Even though I might send an encrypted message to the wrong Alin, Alin will eventually find out. This is a bit confusing because we're both called Alin. So does that sort of make sense? Yeah?
What do you do if you realize that your key is the wrong key?
Good question. So that's really the crucial question. What the hell can you do, right? So this directory impersonated you. In fact, you can't even, here's the problem. If you're Bob here and you see this fake public key, and you go to the New York Times and you say, hey, New York Times, this directory, this WhatsApp directory started impersonating me. And the New York Times can go to the directory and say, hey, directory, why did you impersonate Bob? And the directory can say, no, I did not impersonate Bob. Bob really just asked for a new public key, and this was the public key that Bob gave me. And it's just a he said, they said kind of a thing, right? So it's really sort of an open research area to figure out what's the right way to whistleblow here. So for example, one project that we're trying to work on is there a way to trap the directory somehow so that when he does stuff like this, you get a publicly verifiable a cryptographic proof that he really misbehaved. Right now, there's no cryptographic proof. The fact that that public key is there could have come from the malicious directory or could have come from an honest Bob who just changed his public key. So yeah. So again, a step forward, but we're not there. It's just that there's much more work to do here. And I think you also had a question.
Yeah, couldn't Alice just ask Bob, this is you?
So that's a chicken and an egg, right? So we have Alice, we have Bob, and we have the attacker. Alice asks Bob, is this your public key? Let's say B prime. Let me make this more readable. So attacker, right? So Alice asks, hey, Bob, is this B prime your public key? The attacker changes it. Hey, Bob, is B your public key? Bob says yes. Attacker forwards it yes to Alice, right? Remember, Bob and Alice don't have a secure channel. That's the problem we're trying to solve with this directory, right? So the attacker can always man in the middle people. Well, people like Alice and Bob. If the attacker can man in the middle everything, then there's really no hope. And we're living in a very sad, sad world if that's the case. Yeah. It actually might be the case, but we'll see. Anyway, so I claim here that this is a step forward, but there's still much work to do. Right? So we get transparency, Bob can detect, he'll know, he won't be able to convince anybody, but if a lot of Bobs get compromised, you're still like in a place where everybody knows that something's off and we'll all stop using WhatsApp, for example, right? By the way, WhatsApp is a great tool, you should continue using it. I'm just saying it's difficult to use right. Like if somebody really wants to target it, they can play a lot of tricks to still trick you. So yeah, all right, we already talked about this. And yeah, again, if the directory can equivocate, then all bets are off, because now Bob will look in this directory, he'll think he's not impersonated. Alice will look in this directory, she'll think she's not impersonated, right? So the reason we started this research is because I really my thesis is on building these directories that are efficiently auditable and have a hard time impersonating people. So that's why we decided to look at how could you do this with Bitcoin. Yeah, so of course, there's one project called KeyChat that we're working on with some high school students, and we're using the Keybase public key directory, and we're witnessing it in a Catena log so that stuff like that doesn't happen, right? Okay, so now let's talk about blockchains. In general, people nowadays like to say, I need a blockchain for X, right? I need a blockchain for supply chain management. I need a blockchain for cats, for whatever. I've heard a lot of crazy stories. IoT, self-driving cars, blah, blah, blah. And I think the right way to think about blockchain is to never, ever say that word unless you use quotes, first of all. And second of all, to understand what Byzantine state machine replication is. Right? And if you understand what Byzantine state machine replication is, or Byzantine consensus, you understand blockchain, and you understand all the hype, and then you can make some progress in solving problems. In the sense that, what is blockchain? So it's what we're doing here is we're doing a Byzantine consensus algorithm. We're agreeing on a log of operations. Right? By the way, that's what Catena does too, by piggybacking on Bitcoin. It agrees on a log of operations. Right? But the other thing that SMR, or Byzantine consensus, does is that it also allows you to agree on the execution of the ops in that log. So in Catena, you don't agree on the execution. You just agree on the statements, but there's no execution of those statements, in the sense that you can't build another Bitcoin on top of Bitcoin in Catena, because you can't prevent double spends of transactions that are Catena statements, right? Like the Catena statements, you have to look in each one and tell if it's correct. So to detect a double spend in a Catena-backed cryptocurrency, you would have to download all of the transactions, and because you cannot execute it like the Bitcoin miners do and build this UTXO set. I'm not sure this is making a lot of sense. But let's put it another way. In Bitcoin, you have block 1, and then you have block 2, right? And there's a hash pointer, and there's a bunch of transactions here, right? And remember that what prevents me from double spending something here, like I can have 2 transactions in this block that double spend the same one here. What prevents me from doing that is exactly this execution stage, right? Because in the execution stage, when I execute this first transaction and I mark this output as spent, when I execute the second transaction, I cannot spend that output anymore. Right? In Catena, you can't do anything like that with the statements. You just agree on the statements. In Catena, you would put this transaction in the log, this one, and then that one, and someone would have to detect that the second one is a bad one by actually downloading it. That's kind of what I'm trying to say here. So in general, the way you should be thinking about blockchains is through the lens of Byzantine consensus, and that'll get you ahead of the curve in this overly hyped space, right? Because it's really just this. You're agreeing on a log of operations, and then you're agreeing on the execution of those operations according to some rules. The rules in Bitcoin are a transaction there cannot be 2 inputs spending the same output, right? More or less. There's other things too. Yeah, what that gives you is it allows you to agree on a final state, which in Bitcoin are the valid transactions. That's the final state, right? In Ethereum, for example, the final state are the valid transactions and the account balances of everything and the smart contract state for everything. And I guess you'll learn about that later. So you can build arbitrarily complex things with Byzantine consensus or with blockchains. And the high-level bit, if you want to look at it another way, is that you have a program P, right, which could be anything, could be a cryptocurrency. And then instead of running this program P on a single server, S, what you do is you distribute it on a bunch of servers, S1, S2, S3, S4, right? And now as a result, to mess with this program P, it's not enough to compromise one server, you have to compromise a bunch of them, right? Okay, so, and some of you might also be familiar with this term permission blockchain. So when you distribute this program P amongst n servers, where n is equal, let's say 3f plus 1, and f is equal to 1 in this particular case, in a permission blockchain, this n is fixed, right? Once you've set n to 4, it has to stay 4. These servers have to know one another. They need to know each other's public keys. And only one of the servers, f is equal to 1, can fail. If more than one server fails, then all bets are off. Your program can start doing arbitrary things. In particular, if your program is Bitcoin, it can start double spending. I'm moving a little bit fast, so I'll take some questions up until this point before I go on. Yes?
In a permission blockchain, do they use proof of work?
No, you don't have to. So that's kind of what the hype is about. This stuff, there's like, the first interesting paper on this was 1976 or something like that. So this is 40-year-old research. We've known how to do permissioned consensus. We used to call it Byzantine consensus for 30 or 40 years, right? So there's nothing new there. It's just that it's very useful nowadays to say blockchain than to say consensus, because then you get $10 million from your venture capitalist folks.
You don't have to do proof of work. Do they ever do proof of work?
It would be such a bad idea technically to do proof of work in a permission consensus algorithm. Completely unnecessary. Plus, probably insecure too. Yeah. So now, the reason you do proof of work is because in a permissionless blockchain, this n is not fixed. N could go, let's say n was 4, it could go to 8, then it could go to 3, then it could go to 12. In other words, people are joining and leaving as they please. And the reason you need proof of work in Bitcoin, one way you can look at it is that you're really turning a permissioned consensus algorithm into a permissionless one. And a consensus algorithm is just voting. These n folks are just voting. And you need 2f plus 1 votes to sort of move on, right? And if this n changes over time, like if this n becomes bigger, it's very easy to take over a majority of the voters. If I can just add fake voters to a permissioned consensus algorithm, I can just take over the consensus algorithm. In other words, I can take over more than f nodes, right? So the trick there is you have to prevent that from happening. And the only way to prevent that is to say, look, if you're going to join and make my n bigger, you better do some work so that it's not easy for you to join. Because if you're a bad guy and you want to join, you could do that very easily unless I require you to do some work. So that's kind of the trick in turning a permissioned consensus algorithm into a permissionless one. And in fact, the way these permissioned animals work is completely different than Bitcoin. They're much more complex. Bitcoin is incredibly simple as a consensus algorithm. If you ever read a consensus algorithm paper, it's a bit insane. Also to implement, it's a bit insane. Bitcoin is very simple to implement compared to these other things. I mean, Bitcoin is of course a complex beast as well, but you should look at, let's say, practical Byzantine fault-tolerant paper, PBFT, and try and implement that. So anyway, why am I telling you all of this? The reason I'm telling you all of this is because if you want to do a permission blockchain for whatever reason, one way to do that is to use your favorite Byzantine consensus algorithm. So that would be, let's say, PBFT. This was 1999 from MIT. So you could use that. You could have a lot of fun implementing it. Another thing you could do is you could take your program P and just give it to an Ethereum smart contract. And you know that the Ethereum smart contract, if the Ethereum security assumption holds, it'll do the right thing. It'll execute your program P correctly, right? But the other thing that you could do actually is you could use Catena to agree on these logs, on the log of operations for your program. And then you could use another 2f plus 1 servers or replicas to do the execution stuff so that you can agree on the final state. And this gives you a very simple Byzantine consensus algorithm. So remember, Catena doesn't give you execution. It allows you to agree on the log of ops. To get the execution, you basically take a majority vote. If you see, you have 2f plus 1 replicas, servers. And if you see f plus 1 votes on a final state, you know that's the right state. Because only f of them are malicious. So in fact, if you use Catena with 2f+1 replicas, I claim that you can get sort of a permissioned blockchain that sort of leverages the Bitcoin blockchain to do the agreement on the log of ops. So in that sense, it's sort of a mix of a permission and permissionless. We haven't studied this, like we don't know what properties it would have. So that's future work. If you don't need execution, for example, if all you're doing is you're agreeing on a public key directory, like here, there's no execution, this directory just is supposed to stay append only, we have some research that allows you to prove that every transition is an append only directory. And if you only need execution, you can just use Catena directly, as I already told you guys, for the software transparency application, for the public key directory application. And if you want to do a permissionless blockchain, then of course you would have to roll your own. But you have to proceed with caution there, right? It's not an easy thing to do. OK, so let's conclude now. What we did here is that we enabled these applications to efficiently leverage Bitcoin's consensus, right? So clients can download transactions selectively rather than full blockchain and prevent equivocation, right? And you only need to get 46 megabytes instead of gigabytes from the Bitcoin blockchain. So why does this matter? These are just, I think, the 3 killer apps: secure software update, public key directories. By the way, the public key directories also are applicable to HTTPS. So when you go on facebook.com, you have to get Facebook's public key. The certificate authorities that sign the public keys are often compromised. So they're often fake certs for Google, for big companies like that, and you might use it. But if you have a public key directory, Facebook and Google can immediately notice those fake certs. It's a step forward. And for more, of course, you can read our paper. It appeared in IEEE Security and Privacy 2017. And I'll post a slide on the GitHub too, so there are links there. And yeah, so again, this is the high-level overview of everything. That's previous work and that's our work. The difference is very small. And now we can also talk about other stuff. In fact, I have more stuff to talk, but before we do, I'd like to have a discussion with you guys if you have questions or, yeah.
So could you implement Catena in the actual Bitcoin code? Would that be something that they would want? It seems like it would be a good feature to have. Or is it strictly separate?
Yeah, I don't think you need to. That's the whole point, right? The whole point of the research is how do we use Bitcoin without getting the miners to accept a new version of Bitcoin, without changing Bitcoin in any way. So no, I don't think there's nothing to do really. We're taking Bitcoin as it is and we're piggybacking on top of it. We couldn't change it I mean, there's a lot of things you can do in some sense, but then you get a very different system, very different. We can talk about it more if you want. Yeah.
You were talking about how you can use this system to verify software binaries.
Yes.
And how you want this to run in SPD mode on phones.
Yes.
So how you install software on phones, say through Apple in the App Store,
yeah.
Is there a way to sign the binary that you actually get from the App Store?
I think your question is really about how do App Store binaries, how do you verify App Store binaries? It's a chicken and an egg in some sense, right? Is that what you're saying? Yeah, yeah, you're right. Eventually, I mean, in the best case, wishful thinking would be to say that, look, the App Store does this already for all of the binaries that they publish, right? Allowing the developers to make sure nobody is posting malicious binaries on the App Store for them. Yeah. Yes? So I'd really like to see Keybase run Catena. It seems like a missed opportunity that they don't do this. I'm sure they have better stuff to do, but it would just really easily allow Keybase. Let's say Keybase has a mobile phone app. It would allow that mobile phone app to verify the directory and get much more security. You know, no equivocation as long as nobody forks Bitcoin. Since Keybase is already publishing these digests, but they cannot be audited efficiently on a mobile phone. I mean, they can, but not securely, you know, because full nodes can lie. Yeah. So there's a big problem with everything I said so far, and nobody caught it. So one problem is that What do you do when you run out of funds? Remember I said the lock server starts with 2 Bitcoins. Let's say it issues thousands of transactions, starts paying those $40 fees, and it runs out of funds. What do you do then? Yeah?
You can maybe reload a new transaction with these, because transaction can take multiple inputs.
What's your name?
Rahul.
Rahul. So Rahul is saying you can reload, and that's exactly right. We just have to change the transaction format slightly. We talk about this in the paper as well, but just to demonstrate real quickly. Suppose, let's take a ridiculous example, which hopefully will never happen in Bitcoin, but suppose the Bitcoin fee is 1 Bitcoin. So now I have 1 Bitcoin here, and I have S1 here, right? And now I have 0 Bitcoins here. Right? So 0 Bitcoins in this output. And maybe S2 here. So that would be terrible, right? Now I can't go on. Does everybody see this is a problem? Right? So what Rahul is saying is, look, add another input here, right? And make it take coins from some other transaction, whatever, 20 Bitcoins. And now you get 20 Bitcoins here, right? So you can easily refund transactions. Right? There's a bit more subtlety there in the sense that you don't want to join logs. Let's say if you have 2 logs, GTX and GTX prime, for different applications, right? And they start issuing statements, S1, S2. You don't want to be able to join, S1, S1 prime, these 2 logs to a single log for certain reasons, right? But this doesn't actually allow you to join them, in the sense that, let's say you actually do this and join them, right? So let's say this transaction here came from GTX prime, right? And there was an S1 prime here, and you did this, right? So the problem is this is no longer a valid Catena transaction for this log, because a valid Catena transaction, the first input spends the previous transaction's output. But in this chain, it's the second input that spends the previous output. So I cannot join logs. And this matters for a bunch of reasons that we don't have to go into. So we talked about batching statements. I want to show you guys some previous work. So how did some previous work do this? Since we seem to have a bit of time. Okay, so there was some previous work called Liar, Liar, Coin is on Fire. Have you guys seen this? So the idea here is that it's a really nice piece of work, and lots of people in the Bitcoin community already know about this, and I think it was an idea before the paper, or maybe not, I'm not sure. But Tage has a similar idea. So, for example, suppose we have this authority. Imagine this is a Catena lock server, and it publishes a transaction which locks 2 Bitcoin and locks those Bitcoins to that public key. And this authority sometimes will want to say 2 different things. It'll want to say S and S prime, right? And it'll sign the statements with their secret key. But the secret key that the authority uses to sign statements is also a Bitcoin secret key. It's the same secret key that the authority used to lock 2 Bitcoins, so $20,000 or something. I'm not sure if Bitcoin plummeted since yesterday. Can never be sure. Does the setting make sense? So I have an authority. It issues statements just like before, and it numbers them with I, let's say. And we want to prevent this authority from equivocating. We're not actually going to prevent it. We're just going to disincentivize it, in the sense that if this authority equivocates like this for the same statement I, what I claim is that anybody can then steal that authority's Bitcoin, because equivocating like this reveals the secret key. And the reason it reveals the secret key is because the signature shares the same I here. So how many of you guys, actually you did cover Schnorr signatures, right? So did Tage talk about how to do this with Schnorr?
This is the K reuse attack.
Exactly, yeah.
Reuse and nonce and.
But did Tage cover it?
Yeah.
Okay, great.
Briefly.
So yeah, so let's go over that less briefly. So again, the idea is that if someone observes these two signatures on conflicted statements for the same I, there is this box where you can put the two signatures and get back the secret key. And once you have the secret key, you can spend this transaction and get that authority's bitcoins. And then there's a lot of details to get it right, because you might notice that if the authority does this, before they do this, they might already be spending this transaction themselves, so as to prevent you from taking it. And details on how to prevent the authority from doing that are in those papers. And yeah, and then you know, whoever discovered this can spend those bitcoins. And the idea is that this incentivizes equivocation by locking these funds under the secret key of the bad authority. But it does not prevent it, right? So in Catena, we actually prevent equivocation. We say, if you want to equivocate, you better fork Bitcoin. Here, they say, if you want to equivocate, you're going to lose $20,000, right? But you have to understand, like, this could be a good authority that locked $20,000 here, but the attackers are going to be, they're not going to care about those $20,000. They're just going to steal the secret key, equivocate, and then the authority is going to be left without money. If the authority is the attacker, then this makes sense. But if the attacker is not the authority, then this makes less sense, because the authority is sort of risking their bitcoins on the assumption that no attacker can compromise them. Which, you know, if we could do that in computer science, I wouldn't be sitting here talking to you guys. Okay, so now, how do you do this? So do you remember Schnorr signatures real quickly? An easy way to do this is using Schnorr signatures. And I think, I could be wrong, but I think this new SegWit update to Bitcoin allows Schnorr signatures, right? Yeah, so with SegWit and with Schnorr signatures, you can definitely do this. And the idea is that a Schnorr signature, if you recall, is just K plus H of M, G to the K, let's say S, where S is the secret key, right? So this is a Schnorr signature on M, right? How many recall this, right? And of course, it's not just this. I mean, this is, the signature is really this and this H of M, G to the K. So it's these two things, right? But now I want to show you that if I sign two different things, I can actually get S. But if I sign them in a certain way. So remember what I said before is I would like this authority to sign I M and I M prime, right? And if the authority does this, I claim that I can get the secret key out, but I have to have the same I. So we relax this in a sense that we're not going to use I here. We're just going to use this G to the K. So if the authority uses the same G to the K to sign, then we can extract the secret key. And the way we can do that is, I'll just show you an example. Sig1, it would be K plus H of M1 G to the K. And it'll be Sig1, and I guess the associated hash, let's call it E1, would be H M1 G to the K. Right? Does everybody see this? And then Sig2 would be K plus H of M2 G to the K. So again, you guys are clearly not paying attention. I forgot the secret key. E2 is hash of M2 G to the K. So I'm using the same G to the K and the same K, right? So now how can I extract the secret key? Does anybody see a solution to this? Raul.
It's now just a system of two equations and two variables where like K and S are the unknown variables.
So I think what Raul is saying is that S is just Sig1 minus Sig2 divided by E1 minus E2. Is that right? Yeah, I think so. See this? Because if I subtract this from this, I just get H M1 G to, I'm not going to have space here. I get, let's say it here, H of M1 G to the K minus H of M2 G to the K times S, right? And now I take this here in the denominator and I simplify and I get S, right? So it turns out that, that's kind of the trick that this work leverages, more or less. The only sort of caveat here is that, remember I said there's a position I for the statement, but now I'm saying there's no longer a position, we have to use this G to the K. And how do we map positions to that G to the K is another trick that you have to do, but you can do it. And if you want more details, you can read the paper, and I'm sure Tage will tell you even more details about this. I think the Lightning Network also leverages this trick in some cases. All right, now let's talk a little bit about some attacks if there's time. The most interesting attack would be the generalized vector 76 attack. So this is a screenshot from a paper. Can everybody see this? So the generalized vector 76 attack is very interesting. So you have an attacker, right? And remember, the goal of the attacker is to replace, let's say, this tx1 with that tx2. It's going to show this tx1 to a merchant, saying, hey, I paid you money. And then it's going to show this tx2 to the merchant, sending the money back to himself. So the whole trick is to fork the merchant on this side and then to switch him back to that, right? It's a sort of a pre-mining attack. And this attack is it's much easier to pull on SPV nodes, because what the attacker does is, let's see, he works on this secret chain, with tx1 in it. And at some point, the main chain might take him over, might win. So the attacker kind of gives up and keeps trying. But at some point, the attacker gets ahead, right, in the second chain. He gets ahead of the main chain. This stuff is not posted yet. And let's say this merchant only for some reason, because they're silly, they only need one confirmation to accept this tx1. And for other silly reasons, this merchant is an SPV merchant, right? So let's draw a figure here. So this merchant is an SPV merchant that only needs one confirmation to accept the transaction. So we have the attacker, and we have, let's say, the SPV merchant. Right? And now the attacker sent, this was the main block there. Let's say this was BI. And the attacker forked it. He put TX1 here and then had a confirmation on it, right? So he sends this chain to the merchant. And the other miners haven't found anything yet, right? So the attacker is a bit ahead, so he's pre-mining. So far, so good? Are you all with me? And remember that he really just is showing block headers. So these are not full blocks. He's just showing block headers. They're much smaller blocks, right? 80 bytes. And the blocks are missing, right? So when he shows TX1, he's just showing like a Merkle path to TX1, to the merchant. Are you guys with me? OK, so now he did this to the merchant. And now what the attacker is going to do, he's going to relax, sit back, and post the TX2 to the, give TX2 to the miners. Let's say the miners are here. He's going to post TX2 to the miners. And he'll stop mining, the attacker. He's not going to mine anymore. But he got the merchant to accept the payment, and the merchant shipped the goods. Maybe this is an online purchase. So now the miners, they will find the next block, BI plus 1. They'll put TX2 here. They'll find the next block, and then the next block, and they'll take over. Their chain will be the main chain. And eventually, this merchant will hear about this main chain. And he'll just see the headers, of course, because he's an SPV merchant. So now the SPV merchant just got double spent. Does everybody see this? That I just double spent the merchant. And sort of the fundamental problem here is that the merchant only received block headers. So he cannot take these block headers and broadcast them to the miners, because miners don't mine on top of block headers. Miners mine on top of full blocks. So this merchant has no protection against this if he's doing SPV, if he's accepting SPV payments. If these were full blocks, what the merchant could have done was the following. the merchant would have received the full block here with the transaction in it, right? So again, the attacker got ahead. But now the merchant, because he saw a block, he's going to ship this block with TX1 to the miners, because he's a full node. Full nodes do that. When they hear about a block, they broadcast it. So now the miners know about this block. They're going to continue mining on top of it. And in fact, the merchant will send both blocks, right, to the miners. So now miners will continue building here. So now the attacker has a bit of a tougher problem on his hands. There is still a way to trick even full nodes. Even if this guy is a full node, you can sort of leverage some timing assumptions to still trick the full node. And the details are in that paper over there. But that's one way, because somebody was asking, I think you were asking, Anne, right, about SPV nodes, how they're less secure. And this is one fundamental way in which they're less secure. If you accept payments with SPV nodes, you're really playing with fire, you know. You do need a sufficiently powerful attacker who can get ahead. But yeah. OK, so with that, I think that kind of concludes the lecture. Any final questions? All right, cool. Then thank you guys.